Good morning, good afternoon, and good evening, everyone. Welcome to the iChemy Palm Oil Processing Special Interest Group POSIP webinar titled Hydrogen-Enriched Syngas Production Derived from Co-Gasification of Palm Oil Biomass and Plastic Waste Mixture. I am Dan Yihua, a committee at POSIP. Before we begin, I would like to remind that everyone online will be muted throughout the event by default as a norm to avoid any interference to the presentation. If at any time you are experiencing difficulties in hearing the webinar, please first ensure you have a stable internet connection. If you are still unable to hear, please type in the chat box or raise your hand button and our team will assist you. If you have any questions about the presented materials, please lodge your questions into the Q&A box. All responses will be given by the presenter after the presentation. First of all, I would like to introduce you about POSIP. POSIP is a non-for-profit special interest group under the umbrella of the UK-based Institution of Chemical Engineers, iChemE. We focus on the chemical engineering practices in the palm oil industry. We provide a forum for the exchange of ideas, the sharing of experiences, and encouraging innovation in the palm oil processing industry. But our membership is not restricted to the chemical engineers. Our major activities are webinar, forum, university roadshow, as well as delivering newsletters, awards, and bursaries to the student. If you miss some of our live events, you can always view the summary on our newsletter webpage. Our upcoming webinars will be on Monday, 12th June. It will be presented by Dr. Phua Eng Thon on the enzymatic approach for the production of healthy functional oils. On 26th June, we have Professor Naomi Shibasaki Kitakawa, Chief Technology Officer of Cytochemical Products Institution, Japan, to give a talk on process for simultaneous production of functional ingredient and biofuels from unused resources in the palm oil refinery. All our industry webinars are free of charge and open to all. Lastly, we would like to thank you, our sponsor in 2023, Desmet Malaysia, KLK Oleomas, Malaysia Palm Oil Council, MPOC, and Malaysia Oleochemical Manufacturer Group, MOMG, for their support to POSIP upcoming activities in 2023. Before we move on to the presentation, I would like to introduce you the speaker, Associate Professor Dr. Bridget Ching Lai Fui. Dr. Bridget is an Associate Professor in Chemical and Energy Engineering Department at Kertih University, Malaysia. She obtained her PhD from University Technology Petronas in 2015. She is specialized in the field of green technology, particularly on the conversion of biomass and municipal solid waste to renewable energy via thermochemical conversion, which firmly focus on solving real-world problems, particularly on mitigating climate change and developing clean energy. Now, I would like to pass the floor to Dr. Bridget for her presentation. Dr. Bridget, please.
Okay, a good evening to everyone. I hope you all can hear me loud and clear from your side. And I also share my screen. So is my screen working fine, Dr. Tan Yihua?
Yes, everything is good to proceed.
Okay, thanks. Okay, so today's webinar, I will be presenting on the topic hydrogen-enriched syngas production derived from co-gasification of palm oil biomass and plastic waste mixture. So this topic is actually quite closely related to my PhD work, and I have collaborated with another peer of mine who is working on this area as well. So my PhD work is actually on rubber seed shells and plastic waste, and I also have assisted in some of the research related to this palm oil biomass with plastic waste mixture. So moving on to the next slide. So this is a summary of my background and also my qualifications. So if you would like to know more information about myself, you can refer to these QR codes. So my research interest is particularly on biohydrogen productions, specifically for thermochemical conversions like gasification, pyrolysis, syngas cleaning technologies, and also green technologies. So this is the summary of my presentation outline for this evening. So I'll be covering 4 points. That is the biomass and plastics as a source of fuel and properties. How is it going to be converted into fuels? And what are the various thermochemical conversion that you could utilize with a mixture of plastic and biomass? And a case study which I have conducted with my colleagues from University Technology Petronas, and also another collaborator that is overseas, that is Petroleum Institute during my PhD studies. Okay, a little bit of background about plastic waste. So since my topic is that I'll be utilizing 2 feedstock, one is the plastic waste and the other one is the palm oil biomass, which is aligned to these special group interests. So plastic waste, so you'll be asking, why do we choose plastic waste? So basically plastic waste has been something that we use in a daily basis. And as a result to that, we have produced a lot of these abundant waste, okay, from packagings that we use from plastics and a lot of other materials that we use for commodity, we use plastics. So as a result to that, we have produced a lot of plastic abundantly throughout the whole world. So from this different plastic, we can get plastic waste from LDPE, that is the low density polyethylene. We can have plastic waste derived from polypropylene, polystyrene, that's PS, polyethylene tetrapellate, that is PT, high density polyethylenes, and also polyvinylene chloride. And besides this plastic, there are also other ways that we also generated, like food waste, waste that is derived from glass, and etc. So out of these different type of waste, plastic have attributed 25.7 of the virus multiple solid waste. So this figure is considered very alarming. So we need to find a solutions. How can we actually utilize this plastic waste for value-added products or convert it to energy? So currently, most of the waste that we produce, like food waste, plastic waste, biomass waste, mostly all end up in landfills. So we know that landfill methods will produce hazardous byproducts, and it will also emit toxic gas. So as a result to that, we need to find other alternatives. So the next one also incineration. So most of the time, the method to dispose such waste is through incineration. So incineration is also another alternative that most of the country are using. However, it also produces secondary waste pollutions. So for incineration, there are 3 ways that they segregate the waste, that is in the solid waste disposal or medical waste segregations, and also hazardous waste that's coming from a chemical processing plant. So here, what are the differences in terms of structure and chemical properties? So for different polyethylene types, there are 3 main types. One is the LDPE, that is the low density polyethylene. And then we have this low linear density polyethylene, that is known as LLDPE for short, and the high density polyethylene. So as you can see here, the structure differs slightly different in the molecular structure, and it has a different degree of branching. So the branching increases from LDPE to HDPE. So it means that the HDPE has a tougher structure and is commonly used in a lot of packaging because it's more durable. So the next waste that is abundantly produced besides the plastic waste is also the biomass. So since we are actually residing in Asian region, we are famous for producing agricultural products, like for example, rice, palm oil, coconuts, cones, and etc. So as a result of that, we also produce a lot of biomass from this agriculture production. So in Malaysia, we are targeting palm oil because palm oil is one of our main commodity in terms of exports to other countries. So we are actually ranked second for the world crude palm oil exporter, okay, besides Indonesia. So this is actually attributing 24% of the total global crude palm oil production. So from these statistics here, from this table here, we can see that we will produce different type of biomass from different activities from the oil palm produce. So for example, oil palm plantation will produce mainly on the oil palm fronts and the oil palm trunks. And meanwhile, the palm oil milling, we will produce other types of biomass like the anti-fruit bunch, palm oil meal effluent, also known as pomace, mesocarp fiber, and palm kernel shells. So out of these 4 different types of biomass, that is the EAB, pomace, mesocarp fiber, palm kernel shell, also stands for PKS for short, and oil palm trunks and fronts, we can know that the one that has the highest calorific value is the shell, and followed by the fiber and palm kernel. So for this study, we will be focusing on the palm kernel shells, which is the shell and the palm kernel. Okay, so why we didn't choose fiber? Because fiber has a bit higher on moisture content, which is not very suitable for a fuel source in a thermochemical conversion. So how do we actually resolve these 2 problems? One of the solutions could be coal gasifications or plastic and biomass waste mixture. So it comes from the keyword gasifications. So gasification actually involves a complex thermochemical reactions that actually convert solid fuels to combustible gas. So this combustible gas can be derived from hydrogens and carbon monoxide with an injection of air, oxygen, steam, or the combination of either air, oxygen, and steam together. So why gasification? So we are trying to address some of these common issues that we are facing. So one is that currently we are facing an instability of crude fossil oil price. So this could be one of the potential solutions. And secondly is that we are trying to meet demands for transport fuel, which has been increasing significantly throughout the years. And we also want to try to find a solutions to reduce greenhouse gases emissions that could actually affect our climate. And fourth main reason is that we are actually facing a depletion of crude fossil oil. So this could be one of the alternative of renewable energy that's derived from gasifications. And the fifth one is that we can have a diverse energy or fuel productions that we can actually obtain from these waste material can be obtained freely in our country and also other countries as well. And we could also find solutions of the conventional method, that is the landfill and incineration, which is attributing to secondary pollutions to the country. So what is gasification? So as I mentioned earlier, gasification is whereby you run at an elevated temperature, around 600 to 800, with an injected of limited access of air, oxygens, or it could be with steam. So this gasification will undergo 4 main processes. The first one is undergoing heating and drying. Then after that, it will move on to pyrolysis, which is the absence of air. And then you will undergo gas-solid reactions, which is involving endothermic and exothermic reactions. And lastly, producing gas phase reactions, whereby our desired product is the hydrogen and the carbon monoxide, which actually constitute in the synthetic gas. Nevertheless, we also have other byproducts, that is the methane, and also the carbon dioxide. And also not forgetting, we might also have some steam that is produced, whereby if we inject steam as the gasifying agent in the gasification process. So what is syngas? So syngas is a short form of synthetic gas, which our primary aim is to enhance the content of carbon monoxide and hydrogen gas in the synthetic gas. So meaning that we hope to get a higher percentage of carbon monoxide and hydrogen compared to byproducts like the methane and also the carbon dioxide. So this syngas can be used or can be upgraded to other liquid and gaseous fuels like the synthetic natural fuels, and it can be used as lubricants, ammonia production, and dimethyl ether. So syngas can be produced in various thermochemical conversions like the combustions, pyrolysis, torrefaction, valorization process. However, gasification is said in literature could be one of the most efficient methods to convert biomass and plastic waste to gaseous products. So this is some of the general overview of the different syngas quality. So if you have different syngas quality, you only can apply in different type of applications. So syngas can be applied for fuel gas for turbine, fuel gas for boiler, synthetic fuels, methanol, and hydrogen. So this means that there is certain criteria for these sort of applications. So for example, if we want to focus on hydrogen productions, so it means that our hydrogen to carbon monoxide ratio has to be high. The carbon dioxide is not considered very significant in these applications. And the hydrocarbon should be in low content, same goes to nitrogen, and the steam should be high. Nevertheless, the alkali metal has to be less than 1.0 because this will be associated to slagging in the gasification process, which could cause blockages in the system. Okay, so this will result very high maintenance. So the next one, this is obtained from literature. So hydrogen can be produced in many various pathway and also processes. So we can have biomass gasifications. Okay, so these are some of the data that I obtained from reviews. So as you can see here, different methods like biomass gasification, coal with carbon capture and storage, natural gas with carbon capture and storage, offshore wind, solar photovoltaic, offshore wind, solar, thermal, electrical, and nuclear, they will actually result in a different cost in operations. So as you can see here, this is an overview of the different costs and what is the economical pricing for the different hydrogen that is produced from these different processes. So for energy contained, among the different fuels that has been produced, it is said that hydrogen can produce a very high energy content. That is 120 megajoule per kilogram. So this indicates that hydrogen is one of a good fuel source for any chemical engineering industry compared to other fuels. So let me introduce you to some of the background and also classifications of gasifications, especially those who are very new in gasification area. So gasifications can be produced in using different agents. As I mentioned earlier, it can produce using air, pure oxygen, steam, and hydrogen and steam. So as you can see here, when we use different gasifications agents that is supplied into this process, we will get different heating value gas. So the one that could produce a high value gas is the one that with a gasification agent of hydrogen and steam. So it will range around 20 to 36 megajoule per normal meter cubic. Okay, and the one that is producing the least heating value is the air gasification, because air gasification would not be able to produce a high purity of product gases, okay, compared to gasification agents such as hydrogen steam. So the next one is the heating of the feedstock. So gasification can be divided into two aspects or two setups. One can be done directly heated, okay, or it can be done indirectly, okay. So the next one is that you might also face some issues such as producing other solid waste, such as ash and char. So this ash, if it's not removed properly, it will cause blockages and high maintenance in the system. So you might develop slagging, whereby the ash is being removed in liquid form, and you might also develop non-slagging in the gasifier, whereby the ash is being removed in solid form. So for gasifier types, there are three main types. First one is the fixed and bed gasifier, which is something that is one of the oldest and is very conventional and is commonly used in industries if they want to build a gasifier. So for a gasifier, there are three types. One is the updraft, whereby the flow of the fuels and the gasifier agent is running counter current, and the downdraft gasifier, whereby the fuels and the gasifier agent is running or is being operated in the same directions, and you have the cross draft fixed bed gasifier. And the next one, we have the entrant bed gasifier. And the last one, we have the fluidized bed gasifier, which is the most recent one. And it has more advantages compared to fixed bed gasifier. And I will mention a few of the good points about fluidized bed gasifier in the following slides. So fluidized bed gasifier are divided into two types, which is the bubbling fluidized bed gasifier and also the circulating fluidized bed gasifier. So this is some of the schematic diagram which to distinguish between the fixed bed gasifier configurations and also the fluidized bed gasifier configurations. So as I mentioned earlier, for updraft, you can notice that the fuse and the gasifying agent is running at the opposite directions. Meanwhile, the downdraft gasifier, the feedstock and the gas is flowing at the same directions. Okay, so for the fixed bed gasifier, you have your drying zone, pyrolysis zone, your reduction zone, and also your your gas is coming out, okay, and the ash is coming out at the bottom. And meanwhile, the fluidized bed gasifier, you actually have two types, which is the bubbling and circulating bed gasifier. The only difference between the bubbling bed gasifier and the circulating bed gasifier is the velocity of the air being supplied. So for bubbling bed gasifier, the velocity should be in the range of 2 to 3 meters per second. Meanwhile, the circulating bed gasifier will be run at a higher air velocity that is 5 to 10 meters per second. So as you can see that the solid and fuel will be homogeneously mixed with the gas when you run it in the fluidized bed gasifier. So there are also some advantages and disadvantages when you use different types of gasifier types. So for example, updraft, also known as a counter current gasifier, you will have few advantages. For example, this system is easier to be constructed. It has high char burnout, very good internal heat exchange, means that good heat transfer inside the reactor, and you can actually tolerate fuels or feedstock that has very high moisture content that is greater than 60% and is easily to be scaled up into a commercial scale. But the only drawback is that it is there is a lot of byproduct that will be produced in this updraft gasifier, that is the tar and also other pyrolysis products like the liquid fuels. So this will produce a very high maintenance cost, especially coming from this updraft gasifier. And this tar is something that is very stubborn. It will cause blockages, and then it will cause stickiness that will block in the piping. And this will result a lot of unnecessary blockages along the piping of the gasifier. So this tar is something that we need to resolve in order for us to use this updraft gasifier. Meanwhile, for the downdraft gasifier that is running concurrently, the difference is that it will produce lower tar content compared to the updraft gasifier. That is the only advantage that you can find in the downdraft gasifier. However, there are also other disadvantages or drawbacks that may be associated with this downdraft gasifier. The first one is that it will produce very high ash and dust particles and high exit temperature. So it means that there is high heat loss from the process. It's difficult to be scaled up. And then there will be a restriction in the particle size. And it only be able to tolerate particle size probably 1 to 30 cm and a moisture content of the feedstock around 25%. And fine particles is definitely not going to be suitable for this gasifier. So the next one is the fluidized bed gasifier. So this fluidized bed gasifier actually do resolve some of the issues that we have in the fixed bed gasifier. So for this fixed bed gasifier, it's good and it can offer high throughput capability and it is flexible in handling low density feedstock, for example, plastic waste. And the only difficulties about this fluidized bed gasifier is that it's more difficult in terms of controlling the gas quality. And you might be expecting a lot of or higher amount of particulate being carried away in the fluidized bed gasifier. So you need a cyclone when you have this fluidized bed gasifier in your system. So here is an infographics that I taken from literature that some of the steps and reactions that is involved in the co-gasification of biomass and plastic waste mixture. Okay, so you can see that what's the difference between pyrolysis and gasification process. So for pyrolysis, you will undergo 4 main stages like the drying at a temperature of 100 to 150 degrees Celsius. So pyrolysis will run at a temperature of 200 to 500 degrees Celsius. So at this point, you might be developing some tar, some gases, and then some charcoal. And when you heat it up at a much higher temperature, around 800 to 1200, so this is already known as a combustion process and a crackling process. So from here, you are able to crack your tar. So this is known as a tar crackling process or catalytic cracking if you have catalyst that is involved. And you can also produce charcoal into hot reactive charcoal. So when it runs around 650 to 900, means that a bit lower than the combustion, then one will be known as a reduction process. So in this reduction process, you will produce products like produce gas like hydrogen, carbon dioxide, carbon monoxide, and also steam. And for solid, you might be producing char and ash. So for gasification, if you have a combination of these biomass and plastics, you will have several reactions that is going on inside these reactions. You will have cracking reactions, reforming reactions, combustions, shift gas reaction if you have a steam that is being injected. And from here, you will get different types of gases like hydrogen, methane, carbon monoxide, steam. You have your methane, you have your C2H6 and C3H6 because you have your plastic contains inside your feedstock. Okay, so if you do not have plastic contained, then you will not have a high amount of C2H4, C2H6, and C3H6. So what are the different applications that you could get from biomass and plastic co-gasifications? So from here, you will produce hydrogen gas. So basically, when you have a mixture of biomass and plastic inside gasification, you still can use fluidized bed, downdraft gasifier, updraft gasifier, and entrance bed gasifier. So nevertheless, you need to have a purifier or a refining system to actually increase or upgrade the synthetic gas to ensure that you will have a hydrogen-rich syngas. So this can be normally done with the presence of catalysts. So catalysts, you have commercial catalysts and you have also renewable catalysts that which you could also incorporate in your system, or you could also add in additional enhancer of the syngas into your system. Okay, next one is, this is the infographics, the differences if you want to produce co-pyrolysis of plastics and biomass waste. So basically, if you are undergoing pyrolysis process, you will produce intermediate products like the gaseous products, bio-oil products, and char. Meanwhile, if you are using coal gasification, it will be our primary product is the gaseous product, also known as synthetic gas. So this syngas, which our primary focus for today's webinar topic, is that we will produce methanol fuels, hydrogens through catalytic synthesis and water gas shift reaction respectively. Okay, so although the process is quite close between coal pyrolysis and coal gasification, you can see that you will have a diverse product. Okay, when the operating parameters varies slightly. So these are some of the research that has been done or have been obtained that has conducted in a coal gasification process with biomass and plastic waste mixture. So we have studies that is using poplar wood chips with polyethylene that's running at a temperature of 286 to 985 degrees Celsius with a hydrogen production that is 17.64. So their key finding is that when they inject steam, the hydrogen and carbon monoxide contained or components will increase in the syngas. There are also some studies that use palm kernel shell with polystyrene and running at around 700 and 900 degrees Celsius and producing 5.6 to 13.1 hydrogen productions, which would be polyethylene with the presence of zeolite catalyst. We have 7.92 mole per hour, and coconut shell with high density polyethylene with the presence of commercial catalysts running around 600 to 800. So this one yield a much higher hydrogen productions. And we also have studies with pine and HDPE wood with polyethylene tetrapellet. So there are also other biomass and plastic coal gasification studies that is found in literature, but this one is obtained the most recent studies. Okay, let's move on. So these are some of the technologies that has been found in Malaysia. So this is obtained from literature. As you can see, when we are focusing on palm oil biomass, there are not much studies that is on gasifications. So far, only 4 that is utilizing empty fruit bunch. Oil palm fronds, only 1. Palm kernel shells is 5 because palm kernel shell have high calorific values. So it has a high potential to be used in a gasification process. For Malaysia, there's only 1 study that is using polyethylene. So as you can see, there are still not much studies that are actually utilizing both of this feedstock in Malaysia, especially thermochemical conversion technologies. So let's move on. So I have discussed and explained on the basic background about gasifications and why are we utilizing plastics and also biomass waste, especially palm-based biomass for gasification process. So I have conducted a research together with my other fellow colleagues, okay, when I was previously studying in my previous institute, there's University Technology Petronas. So we worked with a project with Petroleum Institute. So we have produced a paper on synthetic gas that is produced from palm kernel shells and polyethylene waste mixture in a fluidized bed gasifier using catalytic steam coal gasifications. So from these results, I would like to share with you that we have used palm kernel shells and high density polyethylene, HDPE, as our main feedstocks. So in this study, we have blended these palm kernel shells and high density polyethylene in a ratio of 20% of high density polyethylene to 30% with 10% of nickel catalyst in the fluidized bed gasifier. So this is the proximate analysis and the ultimate analysis for these 2 main feedstock that has been supplied into this gasification process. As you can see here, the moisture contained for HDPE is 0. However, you have a small amount of moisture contained for the palm kernel shell. So if you want to compare about the volatile metal, so HDPE has a very high volatile metal. So some of you might be wondering, why do we need to mix HDPE with palm kernel shell? Why not we just run it with pure palm kernel shell? So as you can see that with a high volatile metals, it will be a beneficial for the gasification process. So with the presence of HDPE, we could actually increase the syngas quality. And also by looking at the ultimate analysis, so since our primary product in the syngas is carbon monoxide and hydrogen gas, so our carbon and hydrogen contained in the feedstock plays a very significant role. So for palm kernel shell, so a typical palm kernel shell will actually have around 40% of carbon content and 5% of palm kernel shells. So by adding high density polyethylene as part of the supplement feedstock in the gasification process, you can see that the HDPE and hydrogen content is much higher than the palm kernel shell. So we are expecting that by mixing with the high density polyethylene, we could enhance the quality of the synthetic gas. So nevertheless, we also added dolomite in another fixed separate gasifier feedback reactor in the gasifier system. Okay, so we are using dolomite because dolomite is available, that is cheaply available, and is commonly used and is found to be very effective to convert tar and hydrocarbon to syngas. So there is also another issue that we will be facing in the gasification process, that is the tar produced. So in order to have a cheap material to convert this tar, we use dolomite as one of our raw material. So in this dolomite, we have done some chemical analysis, and these are the key findings of the chemical components that has been found from the dolomite that we use in our present studies. So this is the experimental setup that we use in University Technology Petronas. So basically this setup is run at 2 kilograms per hour. So this is known as a pilot plant scale. So the steam is being injected into the fluidized bed gasifier, which is being increased by the temperature of the superheater. And then from here, in the fluidized bed gasifier, you have a mixture of polyethylene and palm kernel shells with a presence of 10% of nickel catalyst. And then the fixed bed gasifier, which is not drawn here, but is a small that is found in the fluidized bed gasifier at the site, that consists of dolomite, which is used to actually convert the tar into syngas. Okay, so these are the dimensions that the fluidized bed gasifier in this system. So the height is around 2,500 millimeter with an internal diameter of 150 millimeter. So this is representing the gasification zone. And we have the freeboard zone that is 200 millimeter. For the fixed bed gasifier, whereby the dolomite is being placed in the system, is at the height of 2,500 millimeter with an internal diameter of 150 millimeter. So there is 4 individual electrical heater and add thermochemicals that is found in this gasification system. So the process parameter that is involved here is that the reaction temperature is ranging around 650 to 800 degrees Celsius, and the steam feedstock ratio from 1 to 3 has been used. And we are using the mixture blend of polyethylene to biomass ratio that is being placed in the fluidized bed gasifier within 0.2 to 0.3. That is around 20 to 30% of polyethylene out of the whole mixture. So this is the reaction that is involved in the gas when they are being passed through the fixed bed gasifier in the dolomite. So basically the dolomite is rich with these calcium magnesium carbon carbonate. So this is the few reactions that is happening concurrently when the gasification process is run, and the gas that is produced from the fluidized bed passes through the feedstock gasifier that's filled with dolomite catalyst. So here are some of the key findings that we have found. Okay, so the first one is that we have varied the different temperature. So as you can see here, the temperature is being varied at the temperature of 650, 725, and 800 degrees Celsius. And from here also, we have steam to feed ratio of 1 to 2, and also the mixture of polyethylene to biomass or biomass feedstock mixture that is in the ratio of 20 to 30%. So as most of the gasification studies that's found in literature, temperature plays the most significant influence in the product gases in the catalytic steam gasifications. So it gives you the final product composition. So the temperature plays a very important role. So high temperature actually do enhance the syngas productions. Okay, so this is mainly due to the few reactions that's involved. There is the water gas shift reactions, steam methane reformings, and the dry reforming reactions. So these are the few reactions that is taken place during the principal reaction in the gasification process, which is enlisted in these slides here. So when the steam and feedstocks are being varied, okay, so we also notice that it does have an influence for the carbon conversion efficiency. So the carbon conversion efficiency can be tabulated based on the equations that is found here. Okay, so this equation has been extracted from one of the literatures. So as we can see here, by increasing around 650 to 800 degrees Celsius with a constant mixture of polyethylene to feedstock ratio, we could achieve a maximum syngas around 341.08 grams syngas over the amount of 1 kilogram of feedstock that has been supplied in the system. And we have a hydrogen yield of 100.43 gram hydrogen that is produced for every 1 kilogram of feedstock. Okay. And then we also notice that by increasing temperature, we also favor formations like the endothermic reactions. So this is also in accordance to the Le Chatelier principle. So the reforming equations that that's shown below, the two equations, becomes more dominant, and it results to the syngas compositions based on the formulas below. Okay. So for steam to feedstock ratios, so the most is considered one of the influential parameter as well, besides the temperature. So by applying steam inside the gasification agent, the methane and reforming and water gas shift reactions become more dominant. Okay, so these will actually enhance the conversions of the feedstock to the desired syngas productions. So as you can notice here, that when the syngas to feedstock ratio increased to 2 to 3 weight per weight basis at 800 degrees Celsius, the dry reforming syngas yield have increased from 341 to 422 syngas out of 1 kilogram of feedstock. And not only that, the hydrogen yield also shows an increasing trend as well. However, when we increase the steam to feedstock ratio from 2 to 3 at a lower temperature, that is 725, we notice that there is a syngas yield decrease, okay, that is found. And this could actually attribute to the syngas quality degradation. So it means that when the syngas is produced at a lower temperature, the quality of the syngas will also be affected. So you need a sufficient amount of steam, amount of temperature to actually maintain the steam in the gasification process. So let's look on to the next aspects, whereby what happens when the polyethylene waste compositions compound increases in the mixture. So as you can see here, we can achieve around 87.73 volume percentage of syngas when we actually mix the polyethylene with palm kernel shell at a temperature of 800 degrees Celsius, steam to biomass of 1, and polyethylene to biomass of 0.3. So as you can see here, when we increase the polyethylene, this will also enhance the conversion of the solid feedstock, because plastic waste actually converts much easier and faster compared to biomass, okay, because it degrades faster. So these are also some of the methane contains composition and the carbon dioxide compositions that has been produced when the polyethylene and biomass ratio has been increased from 0.2 to 0.3. So it's noticeable that the methane content has been increased from 18.5 to 28.96. However, we also notice that there is a reduction in the CO2 content when there is a Bordeaux reaction that is occurring inside the process. So it means that for Bordeaux reactions, it favors high temperature. Okay, so as a result to that, it will reduce the CO2 concentrations. So these are the optimum conditions that we found from this pilot plant coal gasifications of palm kernel shells and also polyethylene mixture. So from here, we found out that we can get around 86% of synthetic gas comprising of 76.2 to 11.6% of carbon monoxide. So we achieve a carbon conversion efficiency that is 90.2. That is considered very good for our process. So a little bit of an insight, besides doing the hydrogen production, there is also a small research that we have been conducted using these palm kernel shells and also the polyethylene mixture, okay, with the presence of renewable catalysts. So this is one of the side research, but I would like to share with you all as well in this webinar. So this is collaborated with few of the institute as shown here. So from this research here, this thermogrammetry analysis will help us determine the kinetics and the thermodynamics analysis. So from here, we are able to understand what is the energy contained, the minimum activation energy contained to actually utilize in these thermochemical process when we use these two feedstocks together. So these are the general key findings. I will not go into detail on the experimental procedures and also the discussion, but this is just a sharing session on the key findings of the average activation energy that has been found when we are using palm kernel shells, polyethylene, or we have a mixture of palm kernel shells and polyethylene in the ratio of 20 to 80 and 80 to 20. As you can see that when we actually mix it with polyethylene, the energy level seems to be increased, okay? And it falls in between the polyethylene, the palm kernel shells and the polyethylene pure feedstock. So from these key findings, we are able to see the enthalpy energy and the Gibbs energy were found to be in the positive values. So indicating that the process is endothermic and is non-spontaneous in nature. And it could be utilized as one of the potential feedstock for clean energy productions. So let's move on to some of the challenges that is faced and the future prospect. So nevertheless, gasifications, although there is a lot of studies that is going around the world and there is so many research that has been published online. However, this gasification process is still said to be not fully commercialized. Okay, most of the studies related to gasification is still in a research and development stage. So there are still some challenges that we are still facing. And the few of them and the few reasoning is that there is a removal of CO2 from product gas is still not economical viable. So there is still, we still need to find alternatives to how we can actually remove this CO2. And the next one is that we are still producing tar. So this is something that is very problematic in the gasification process. So we need to find a solution, a more economical way, a more sustainable way to actually convert this tar into a value-added products. And most of the catalysts that has been used in gasifications, especially in industries that is producing the fossil fuel hydrogen produced, they are actually using a commercial catalyst like nickel. So those are actually very expensive. So currently those renewable catalysts are still not very comparable in terms of performance in producing high syngas and gasification efficiency. And we are still facing higher cost of fuels, okay, compare from gasification process to fossil fuels. And there is not very much interest from private sectors to actually invest in this sort of process at the moment. Okay, so what are the future prospects? So the future prospects is that we could consider to use adsorbents to actually capture the CO2 at a higher temperature. We can consider using renewable catalysts or implementing the renewable energy, renewable catalysts with other alkali metals. Okay, we could also consider simulator to actually run the process parameter process of the gasification process using OGA techniques. Okay, so basically running these research studies is still very expensive. And the next one is that we should also find alternatives to build or develop new catalysts in substitutions of the conventional catalysts like nickels and ions. And also there will be a consideration of having co-generations of power and fuels to actually reduce the cost and solve power issues. And hopefully we have subsidies of encouraging to promote biofuels in our country, and also having some government initiative to move towards biomass technologies. So in my concluding remarks, these are the key findings of the hydrogen that is produced from my team. Current findings of the co-gasification of palm kernel shells and polyethylenes. And these are the optimized conditions that has been found. And we also found out that with the presence of polyethylene in the mixture, it does enhance the syngas and hydrogen productions. And from the kinetics and thermodynamic analysis, it also reveals that these two feedstocks is a potential feedstocks for clean energy productions. Okay, so I have reached the end of my presentations. So if you would like to know more about this research, or you would like to collaborate, or you wish to contact me personally, these are my contact details. So thank you very much for listening, for the participants have attended these sessions. Yeah.
Thank you very much, Dr. Bridget, for your insightful presentation. Now we open the floor for Q&A. I may start with the first question. How the value chain look like for the gasification? For example, will this fit into the hydrogen economy as green energy, and who can participate in this gasification technology?
Okay, thank you very much for this question, Dr. Tan Yi Hua. Okay, so basically for these value chain, so since our feedstock is on plastic waste, so it could be also can also target from parties that is actually dealing with these plastic waste like the incinerator, instead of burning it directly in incinerations and also for landfill. we could also encourage our stakeholders to actually invest to convert these plastic waste into fuel source. And also we can also target the palm oil mills, because currently they are using it like the palm kernel shell as a boiler applications. So they could actually extend this process for a gasification process. So since they are producing palm kernel shells, they could also supplement with plastic waste as well to actually enhance these synthetic gas. So there are also other commercial companies or industrial companies that are producing hydrogen, but probably using their own conventional methods and not utilizing these gasifications like Toyota, Hyundai, Linde, Liquid Airs. So they could also do like a comparative techno-economics to see which one is comparable. So definitely the conventional method is still much more feasible compared to these existing process. So for these feedstock like palm kernel shells and plastic, right, we could also extend to probably in the rural areas whereby they are probably doing some plantations. And from there, we could also educate this group of people how to actually generate electricity at the lowest, at a lower scale instead of for industrial scale or for household. So this could be a targeted parties to introduce this system to them. Yeah, that's all from me, Dr. Tan.
All right, thank you very much, Dr. Bridget. A follow-up question. How is the study being done on entrained bed reactor? Have you done any study on this type of reactor?
Thank you for your question, Dr. Tan. No, I have not done on entrained bed, and I'm not very familiar what is the advantage of using entrained bed. But we selected the fluidized bed because our feedstock is, we have a combination of light and heavy feedstock. So up to date, fluidized bed is still recommended among the other gasifier reactor. Yes. Okay, I pass to you back, Dr. Tan.
Okay, then the next question will be, if off-draft fixed bed can handle up to 60% moisture, is it able to handle mesocarp fiber?
What I have read so far, I noticed that there are some studies on using this updraft, using this fiber. Yeah, it could be used, and I think it's practicable to use updraft for mesocarp fiber.
Next is, what are the main reasons for little investment or participation from private sector, especially from palm oil players, to involve in the gasification?
Okay, how do they get involved? Is it, Dr. Tan?
No, it's the reason why there are a little bit investment and participants from the private sector to get involved in the gasification industry.
Okay. Okay, because I don't really collaborate very much with palm oil, but I think the main reason why, the few reasons why they are not so invested in this coal gasification is because they, for this process, you require a lot of energy inputs into these gasifications. So when you require a lot of energy, means that are you able to deliver the output energy? So from this process here, the amount of energy that is required to produce the hydrogen to run it commercial viable inside the palm oil industry, is it feasible? So this is something that is still a challenge for this process, for this gasification, because that's why, as I mentioned earlier, this gasification is still require a lot of research and is still not very convincing in the palm oil industry because of the energy requirement. Okay, it's not very sustainable to produce the hydrogen. So the hydrogen that is produced in the conventional methods probably is much cheaper than produced from this from this co-gasification process. Yeah, that's all from me, Dr. Tan.
Thank you, Dr. Bridget. Is there any workable scale-up or industry-scale gasification plant in Malaysia?
From my general knowledge, I think there is one in West Malaysia. That is what I heard from, but I have not, I might be wrong. But most of it is, most of the studies that is found is actually pilot scale. Yeah, so I heard that there is one, but I might be wrong. That is in West Malaysia. There is a gasification plant.
All right. May I know how to deal with tarry syngas from palm biomass? As in, there are many tar content in the syngas.
Okay, so the tarry gas is something that is very stubborn and it contains very high phenols. So one of the methods to actually convert this is to run it at an elevated temperature. So to allow tar cracking. Okay, so this will actually convert it to gaseous products. Or another method is that you can run it at a much lower temperature, around 500 to 600 degrees Celsius, which is lower than gasification, with the presence of catalysts. So there are many commercial catalysts that is involved. You can utilize that. So as I mentioned earlier, catalysts, especially those commercialized like irons and nickels, they are very expensive and they have a tendency to be deactivated. So this is another concern to be taken into account when converting this tar. So normally what we would suggest is that the tar, we hope that the gas that we produce from the syngas has to be at a certain temperature so that the tar will not be in liquefied form. So it will be converted into gaseous. So the amount of tar produced at the outlet of the gasification will be less.
Thank you, Dr. Bridget. Can you comment on the new application and technology that could be beneficial to industries as well as commercial players in Sarawak?
Okay. The new technologies. Okay, thank you, Dr. Tan. So in Sarawak, they are focusing, they are actually moving towards hydrogen productions. And one of it is using these electrolysis. So gasification, I think, is still not yet very, how to say, it's not really the hot options for Sarawak, but they are moving towards these electrolysis. Yeah, so I think by creating more awareness that we have researchers that is working on this thermochemical, would be good to inform these Sarawak government initiative on this.
Thank you, Dr. Bridget. The final question here. From the insightful presentation, a fluid-based gasifier has flexibility to handle different solid density. For a mixture system like biomass and plastic, would the difference of solid density among the material affect the performance? If yes, is there a rule of thumb for the maximum density difference between the solid?
Okay, thank you very much, Dr. Tan. Yes, density the density will play a significant role depending on which type of gasifier you want to use. But in terms of the gas composition that you're going to produce, if you're using the similar feedstock, but different density, I believe the gas composition would not differ very much. So the density plays a role in the gasifier that it could be mixed homogeneously. So some of, because now we are having combinations of different mixture, like plastic is in a lighter density, and the biomass is the palm kernel shell or any other biomass, which is much heavier. compared to the plastics. So with a two dual different type of density, so we need to have proper selections of a gasifier to ensure that it does not create blockages when the gasifier is being run. And also there must be a homogeneous in the mixture, because when you have a lighter feedstock, probably is not going to be mixed well. And as a result of that, you might not have a very consistent gaseous product that's being produced. So one of the solutions to these, if you have like binary mixture or ternary mixture, it will be good to actually pelletize this mixture in a fixed percentage, weight percentage, or you can say mass ratio.
All right, thank you very much, Dr. Bridget, for your insightful presentation. Ladies and gentlemen, we finally come to the end of this seminar. I would like to thank so much to Dr. Bridget for an informative presentation. Our upcoming webinars will be on Monday, 12th June. It will be presented by Dr. Phua Antong from University Technology Brunei with the presentation titled Enzymatic Approach for the Production of Healthy Functional Oil. Next, I would like to thank everyone for your participation in today's webinar. If you have any additional requests, kindly fill out the survey form. Hopefully, the seminar will be beneficial for everybody, and I wish you all a blessed day. Thank you and goodbye.